Hello guys. In this video, I'm gonna shed light on one of the examples, very good one, and very insightful. So we learned in this chapter that some systems of linear equations might have many solutions, infinite solutions, might have just unique one solution, or even no solution at all. Okay, basically no solution means there is inconsistency in the systems of the equations. Okay. So in this example here that you can see guys on the screen, it parameterized basically this kind of system. So you have the system, and based on two parameters, A and B, this system can be of infinite solutions or one solution or no solutions at all. Okay, so it's our rule here to find possible values for A and B such that the system has many solutions or one solution or infinite number of solutions. Okay, so I'm gonna here solve. We have in the question just four examples. I'm gonna pick one of them, which is D, and solve it with you guys here. Okay, so the system is X plus Y equal to 1 and 2x plus y equal to b. So basically, x and y here is our unknowns. So it's either we can find unique solution or unique value for x and y, or infinite values for x and y, or no solution at all. Basically, we cannot solve x and y through that system based on the value of a and b. Okay, so let's write the system in a matrix form to make it easy. A, 1, then 1, 2, 1, then B. Good. I'm going to divide the first equation by A. So the first element here will be 1. This will be divided by A, so it will be 1 over A, 1 over A, 2, 1, B. Okay? Then I'm going to multiply the first row by 2 and subtract, this new row from second row. So the new row R2 new equal to R2 old, row 2 old minus 2 R1. This is R2 old, and this is basically R1, row 1. Okay, so if we do that, what's we're gonna have? So the first row will not change. The second row will be R2 new, which is R2 minus 2 R1. So if you multiply 1 by 2, it will be 2. So 2 minus 2 will be 0. If we multiply 1 over A by 2, it will be 2 over A. Then when we subtract, it will be 1 minus 2 over A. And then we're going to multiply by 2 again, 1 over A. So it will be 2 minus B, 2B minus 2 over A. B minus 2 over A. Good. Then we're going to stop here. Okay, we're going to stop here. We will not continue. Okay, our Gaussian elimination. And just look at this like final equation here. Okay, and write it in its normal form. So 0x1 plus x2, 1 minus 2 over A equal to B minus 2 over A. Okay? And you can abbreviate it further or reduce it further. So 1 over A, 1 over A. You can multiply like 2. You can multiply A by basically that row. So this will be 0. This will be A minus 2. This will be BA minus 2. Okay. So that equation basically will be 0x1 still plus x2 A minus 2 equal to AB minus 2 or BA minus 2, whatever. It's the same. Good. Now let's look at this equation, because from that equation we can determine, basically based on assumptions on A or B, if this system has many solutions, or one solution, or unique solution, or no solutions at all. Okay, so let's start by the most easy one, no solution. Okay, so for no solution, basically there should be some inconsistency in the systems that you have. So in the no solution case, inconsistency means that 0 minus value, like 0 equal to 2, for example. This of course cannot be. Okay, so in that case, to create that case, A should be equal to 2, and in that case this element here will be 0. But at the same time, BA or AB shouldn't be equal to 2. So BA is not equal to 2. Okay, so if we write this down here, this is a system, the new system, this will be 1 over A, then 1 over A, and this will be 0, this will be 0, and this will be BA minus 2. Okay, since A equal to 2, so we can just remove A here. So this will be 1 over A, 1 over A, 0, 0, and basically 2B minus 1. That's fine. You can even keep it B minus. So what we have from that equation, or that equation, whatever you like, is that 0x1 plus 0x2 equal to 2B minus 1. Or even AB minus 2, whatever. So that means 0 equal to something, which is of course not valid at all. Okay, so basically there is inconsistency here, so the system has no solution. Good. The second case, I'm gonna start here by the case of of infinite solutions. Okay, so we start by no solutions, and now we go to the opposite case, infinite solutions. In the opposite case, again, E equal to 2. Okay, but in that case, A and B equal to 2. And in the all examples that you're gonna see, we have here like 4 examples. Remember, I just solved one of them. Okay, you're gonna find that the difference between the no solution and the infinite solution is just one assumption. I mean, here we have 2 conditions in the no solution case, that A equal to 2 and AB doesn't equal to 2. Here both equal to 2. So it's a change in that one, in that condition. Just flip it. Okay, so when you flip that second condition or the first condition based on the examples, you're gonna find that you transfer from, or you are going from no solution case to infinite, or vice versa. No solution, infinite solutions to no solution. So when we assume A equal to 2 and AB equal to 2, let's now write the system again. If we do that, the system will be 1 over A, 1 over A. No problem. But now the second row will be 0. A equal to 2, this will be 2 minus 2, which is 0. And then BA minus 2, and AB now is 2. So this will be 2 minus 2 again equal to 0. And if you remember, guys, when you have like one of the equations completely 0, and now the remaining equation, just one equation with 2 unknown, in these cases, when you have less equations than the number of unknowns, we can assume one of them as a parameter and basically find the other using this parameter. So what I'm gonna do here, I'm gonna assume that x2 equal to t or s, any variable, whatever. So in that case, x1 plus 1 over a multiplied by x2, which is t now, equal to 1 over a. So from that, x1 will be 1 over a minus 1 over at. Or you can say 1 over a, 1 minus t, yes. And if you want to go further on that, from these two equations, A equal to 2, right? We have A equal to 2 and AB equal to 2. So 2B equal to 2. So basically B is equal to 1. We even find like A and B. So we can go back to that equation and find basically x1 again. So x1 will be 1 over A. So it's 1 over 2, 1 minus B. Okay? So these are infinite solutions. Why they are infinite? Just put this into like a box here. We can assume x2 equal to 0. In that case, x1 will be half 1 minus 0. It's a half. This is the first solution. Assume, for example, x2 equal to, let's say, 1. So in that case, x1 will be a half, 1 minus 1, 0. Another solution. And so on. You can assume x2 was whatever value. And you're going to get another, a different, generally, x1. Okay? That's why we have infinite solutions. Okay? Finally, the last case, which is the unique solution case. In the unique solution case, basically what you should do, you shouldn't have a 0 here or a 0 here. Okay? I'm sorry, you shouldn't have a 0 here. You can have 0, that's fine. Okay? But you shouldn't have a 0 here. Okay? So basically what we're gonna do, we're gonna go back to this equation here, which we did use when we find the last step in our Gaussian elimination before we go further in the cases. So we have 0x1 plus x2 a minus 2 equal to ab minus 2. So basically x2 a minus 2 equal to ab minus 2. So x2 equal to ab minus 2 divided by a minus 2. And in that case, a doesn't equal to 0. This is very strong condition here. If a equal to 0, this will lead us to either a no solution case in which AB doesn't equal to 0, or infinite solution case in which AB equal to 2. Okay, like what we find here. So when we start by A equal to 2, when we assume AB equal to 2, we get like the infinite solution case. When we start by A equal to 2 and BA doesn't equal to 2, we get into the no solution case. Now we assume an opposite case. So A doesn't equal to 0. A doesn't equal to 0, so this should have a value like 2, 1, 0 even, that's fine. Okay? It will be 0 if AB equal to 2. And from that, we can find basic x1. So we have x1 plus 1 over ax2 equal to 1 over a. So x1 will be, sorry, x1 plus 1 over a, ab minus 2, a minus 2 equal to 1 over a. So a1 is equal to 1 over a minus 1 over a, ab minus 2, a minus 2. You can reduce it further, just take like a common factor or whatever, but you can just leave it there. That's fine, That's very fine. And that's a unique solution. Once a doesn't equal to 0, you have a unique solution. Like let's assume a equals to 1, for example. We don't know a, of course, So in that case, x2 will be ab minus 2, so b minus 2. And x1 will be 1 minus ab minus 2 over minus 1. Oh, I'm sorry. So if a equal to 1, x2 will be will be minus b plus 2. Sorry for this. Yeah. Okay. So, and then here also we should correct this because a now is 1, so we should remove this. Okay. So we have 1 plus b minus 2. So x1 will be b minus 1. That's a unique solution. If you put b equal to 0, x2 will be 2, x1 will be minus 1, and so on. Okay? It's still parameterized, but based on A and B. Okay, we're going to find unique solution. Okay? So let's summarize what we did. So based on our last equation in our Gaussian elimination, 0x1 plus x2, we finished the problem. I'm just summarizing what we did. x2 a minus 2 equal to ab minus 2. That's the equation that we end up with. Based on the value of a, we make some assumptions on ab, and we have 3 cases. We can start using the following. Based on a, if you assume a equal to 2, of course, this is based on the notion here that x2 is multiplied by a minus 2. That's the driving force for us. If you assume a equal to 2, then you have another 2 cases. The first case, ab equal to 2, that will give you infinite solutions, many solutions. If you assume that ab doesn't equal to 2, that's a problem, because you're going to have a 0x1 plus 0x2 equal to something. 0 equal to 4, for example. That doesn't make sense. It's inconsistent equation. It's a wrong equation, actually. And from that we get no solution case. Now the other case for a is a doesn't equal to 2. Whatever b is, b can be 0, plus 1, minus 1, 0.1, million, whatever. Okay, in that case we get the unique solution. Okay, guys, and we can build this flow chart basically, or tree, okay, in any of the examples in that problem. Okay, guys, thank you very much for watching, and see you in another video. Bye-bye.